Okay, guys, here's what we need to do today. Here are some of the IB syllabus objectives that we're going to try to cover. Hopefully, we will be able to determine the direction of the force on a current-carrying conductor that is placed in a magnetic field. That'll be one thing. We should be able to determine the direction of the force on a charge moving in a magnetic field. I'll teach you how to do that. And we should be able to solve problems involving magnetic fields, magnetic forces, and currents. All right, so let's remember right-hand rule number one. Right-hand rule number one allowed us to determine the direction of the magnetic field that was created by a current-carrying wire. You guys remember that one? What did the magnetic field around a current-carrying wire look like? What was it shaped like? It was circular, just circular magnetic field. And the right-hand rule, the first right-hand rule, told you what direction it was going, right? Either clockwise or counterclockwise. If you grabbed the wire with your right hand so that your thumb was in the direction of the conventional current, your fingers would curl around that wire, the direction of the magnetic field that wire created. All right? If I took that wire, instead of it being straight, I made a loop out of it, what was the resulting magnetic field pattern? It was like a bar magnet. Okay, remember that? We talked about this stuff last time a little bit. So here's a looped wire with current going through it. If I use that right-hand rule, no matter which way the current's going, notice I get this type of a magnetic field, which is very similar to what you would expect from a bar magnet. Yeah? Right here, if this was a bar magnet, what magnetic pole would that be? North or south?
North.
Notice the field lines are going away here. Field lines go away from north and towards south. When we're talking outside of a magnet, the field lines go from north to south. Inside of the magnet, they go from south to north. Because technically the field lines make a complete loop. Okay? Yes. Let's think back. First of all, let's think back to the last time I saw you, which was just 2 days ago. But also, let's think back to the 1820s. That ancient famous physicist, Cortlandt, whose name was Hans Christian Ørsted. Hans Christian Ørsted, you remember him? Remember he did an experiment to prove the connection between electricity and magnetism? And I showed you that experiment right here using an overhead projector. The wire. And so what did he do? What did he do? Okay. So what was that showing? I see you as about saying. What was that showing? Well, let's think about it. He put current through a wire, and the needle, the compass needle, moved. So what did he show that a current-carrying wire does? Creates a magnetic field and exerts a force on a magnet. Okay. A current-carrying wire will exert a force on a magnet. That's what Hans Christian Ørsted showed. Let's think back to Newton's third law. What was Newton's third law?
Equal and opposite reaction.
Excellent. Every action is an equal and opposite reaction. As Renee was saying, if you punch something, it punches you back. Equal and opposite. So now let's put that law, Newton's third law, in the context of Ørsted's discovery. Ørsted said a current-carrying wire exerts a force on a magnet. That's beautiful. That's what Newton would tell us, that a magnet should exert a force on a current-carrying wire, if that's true. And lo and behold, it is true. Okay? If I take a current-carrying wire and I place it in a magnetic field, that wire will feel a force. Okay? So we just kind of reasoned that if I have a current-carrying wire and it's in a magnetic field, it will feel a force. The question that I know is just burning in your minds is, what direction is that force, I wonder? What direction will it feel a force? And this is where we learn our second right-hand rule. And it is the most exciting of the right-hand rules, and potentially the most confusing. But here's how it works, okay? If I have a current-carrying wire, and I take my right hand, and I point my fingers the direction of the conventional current, so I point my fingers the direction of the conventional current, and it's in a magnetic field, and I keep my fingers pointed that direction, and I rotate my hand until my palm is aiming the direction of the magnetic field. Okay, I'll show you it. And then I stick out my thumb. That's the direction the wire will feel a force. Okay? Okay? So, the book, I know the book does it differently, and I don't like the way the book does it. But I'll talk about how the book does it, and you might prefer that way. But this is the way I like it. So, yeah. So here's right-hand rule number 2. You take your right hand. First of all, it must be your right hand. Remember that, okay? You point your fingers in the direction of the current that the wire is traveling. the conventional current. And keeping your fingers pointed that direction, there's two possibilities. And again, many books explain it slightly differently. You'll rotate your hand until your palm is in alignment with the magnetic field. Your palm is pointing from north to south, or in the direction of the magnetic field. Another way of thinking of that is you would align your hand so that if you bent your fingers, curled your fingers, they would then point the direction of the magnetic field. That's one way of doing it too. So straight fingers is current, bent fingers is field. Your thumb will then be the direction of the force that that wire will feel.
So it's kind of like thumbs up.
Yeah, kind of. Okay? Does that make sense? All right, let's look at a picture in practice. Here's a picture. Let's look at just this picture A over here for a second. Here I have a horseshoe magnet. Notice that it creates a magnetic field from left to right, from north to south, inside of the horseshoe part. Here's my current carrying wire, conventional current going from positive to negative. If I take my right hand and I point it the direction of the current, keeping my hand pointed the direction of the current, I rotate my hand until my palm is going the direction of the field, which is this way. Then I stick out my thumb, and that is the direction of the force, which is downward.
How do you know why does it feel like that?
Because the field is going this way, from north to south, and that's the direction you want your palm pointing, if you can point your palm. Okay? All right? Notice that if I reverse the current, try it reversed. If the current's now coming out of the board and the field's still going from left to right, then the force is up. Okay? Let's do some more practice just to make sure we have it good here. Let's imagine I have a current carrying wire with the current going up. Okay? And I place it in a magnetic field like so. Ooh, I didn't mean that, but we'll go that way. I was thinking in and I drew S. Fingers, direction of the current. Rotate your hand until your palm is the direction of the field, which in this case is from north to south. So it's coming straight out of the bore. You would say the force is coming straight out of the bore. Yes. Let's try another one. Let's imagine, I'm going to make this one hard. This is going to be tricky. The current is coming out of the board. There's a wire coming out of the board. This is why I'm making it tricky, because now you got to stick your fingers and point them towards yourself. And the magnetic field is going. Okay, what direction is that wire feeling a force? Okay. It's feeling a force to the right. Yeah? We need more practice, or are you okay? Now that you've learned right-hand rule number 2, which tells you the direction of force on a current carrying wire in a magnetic field, you're probably thinking, that's pretty cool. But what I really want to know is, how strong is that force? And then you're thinking, well, this is physics, so there must be an equation. And I'm going to say there is an equation, and it will tell you the strength of the force on a current carrying wire in a magnetic field. But before I even show you the equation, brilliant. So what are some factors that will affect the strength of the force on the current carrying wire?
The current.
Okay, how much current's in the wire? The length of wire that's in the field and the strength of the magnetic field. Beautiful. Here we go. So here's the equation. F equals BIL sine theta. Now you guys just did that at the beginning of class, so you are either telekinetic or you've done some work or something. Here's our equation to help to determine the magnitude of the force on a current carrying wire. B stands for magnetic field strength, measured in teslas. Okay? 1 Tesla happens to be a very strong magnetic field. The Earth's magnetic field is about 50 thousandths of a Tesla. A bar magnet that you guys were playing with the other day with iron filings is about 100th of a Tesla. So a 1 Tesla field is a significantly strong magnetic field. Tesla coil is something else. Okay, I. What does I stand for? Current, measured in amps. L stands for length, measured in meters. And sine of the angle is the angle between the wire and the magnetic field. When the wire is perpendicular to the magnetic field, what's the angle? 90. Sine of 90 is 1. So that is when the force is going to be the strongest. You will get the most force in your wire when it is perpendicular to the magnetic field. Any other angle, you will get less force. All the way down to the point where the wire is parallel to the field, what would the angle be? We talked about that earlier. 0 or 180, and therefore this becomes 0, and therefore this becomes 0. A wire feels no force when it is perpendicular to a magnetic field, a current carrying wire. Parallel is what I meant to say. Okay, so now I know what you're thinking. See, this is my telekinetic psychic day. You're thinking, why do I care? What's the point of all the stupid wires, magnetic fields, forces? I don't care about that. And I would say you do care. You just don't know you care yet, because all of you at some point in your lives have listened to music. And if you've listened to music, this is why you've listened to music, whether you know it or not, okay? This is how we make sound come out of speakers. This is how we make devices called galvanometers. This is how we make electric motors. The fact that a current carrying wire feels a force when it's in a magnetic field has allowed us to create electric motors. So if you drive a Prius, if you use a blender, if you've ever used a vacuum cleaner, any device that has an electric motor works because of the fact that a current carrying wire in a magnetic field feels a force. But let's go back to music for a second. If you listen to music, this is how we create sound. Okay? Have you ever seen a speaker? You know, if you take the covers off of the speaker, you'll see these big cones. There's big ones and mediums and smaller ones, okay? Woofers and tweeters and mid-range little cones in there. If you take apart the speaker, you'll notice that it has a magnet in the back of that cone. Now, this is a very simplified version, but it's going to give you some ideas. So notice this magnet is not your traditional horseshoe magnet. It's actually like a three-pronged magnet. They might call it a trident magnet. That's what I would call it, because it looks like a trident. Okay, notice you have north pole in the middle, south poles on the edges. So we create these magnetic fields going from the middle bar towards the outer bars. Everybody with me so far? Now, this is a cross-section. So I've sliced the cone in half. This cone, if you've never seen one, they're made out of like kind of cardboardy material or flexible material. And in the back of the cone is a cylinder. So this is a cylinder chopped in half. And I take that cylinder and I've wrapped wire either in the cylinder or around the cylinder, okay? And now I put current through my wire. So here's my current. It's going, in. And since this is a cylinder, notice that all the wires up here, the current is going into the board. But as it wraps around, those same wires bring, oh, gosh. As I was saying, those same wires, when they wrap around, they're bringing current out of the board. You see how that's going? So current's going like this? Everybody with me? Now, using the right-hand rule you just learned, forget about these bottom wires. Let's look at these top wires that are in a magnetic field that's going from bottom to top. What direction do all of those wires feel a force? The current is going into the board. The field is up. All of these wires are being pushed that way. Yeah? In agreement? Now, the same current carrying wires, when they come around down here, notice now the current's coming out of the board and the field is down. What direction do they feel a force? Same way. So in this scenario, the cone is being pushed outward. You with me? Then I instantaneously flip the current, so it goes the opposite direction. Then what happens? All these things pull a force inward, and the cone comes back. And then I flip the current back and forth at a very specific frequency so that my cone vibrates at a very specific frequency and creates waves at a very specific frequency, which we hear as sound. Okay? Isn't that cool? Okay. He does. That's a big ear. Okay? So now we know how sound is made in speakers, which is kind of neat. We can also we can now come up with a more concrete definition of magnetic field. We've talked about the direction of the magnetic field being the direction that a compass needle will point, but we don't always have a compass. So another way that magnetic field is defined is by the direction that a current carrying wire will feel no force. Okay? If you have a current carrying wire and you rotate it around, the direction where it is no longer feeling a force, you know that that wire is now parallel to the magnetic field. Okay? Another way of saying that is a current carrying wire feels no force when it is parallel to the magnetic field. And now if I have a current carrying wire and I measure how much force that wire feels, it's basically telling me how strong that magnetic field is. It's another way of defining the strength of the magnetic field. It basically is F over IL. It's just a rearrangement of that equation where F equals BIL. When I arrange my wire so that it's feeling the maximum force, or in this case it's perpendicular to the field, if I divide it by the current through the wire and times the length of the wire, that is another way of defining magnetic field strength. So let's think about this for a second. Now I know that a wire that has current through it in a magnetic field feels a force. What happens if I turn off that current? Will that wire feel a force? No. Okay, so it's the current carrying wire that feels the force. And what is current?
It's electrons, it's charged particles moving through a wire.
Excellent. It's charged particles moving. So if that is true, if current carrying wires feel a force, then I would imagine that if I forget the wire, what if I just took charged particles and moved them in a magnetic field? Then they should feel a force too. And lo and behold, they do. So if I take protons or electrons or other charged particles and I throw them in a magnetic field, they'll feel forces. And the strength at which they will feel a force is determined by a couple of things. What do you think that's determined by? How charged they are, the strength of the field, and how fast they're moving. Excellent. Okay? QVB, right? F equals QVB sine theta. Very similar to ILB sine theta, okay? Q is how charged the particle is. V is how fast the particle is moving. And theta is the angle between the motion of the particle and the magnetic field. We use the same right-hand rule we've been using with one little twist, which I'll tell you in a second after you've written all this down. Now, this equation allows me to figure out how much force that particle will feel. The right-hand rule will allow me to figure out the direction of force that particle will feel. And it's just the same one as you did before. You take your fingers, you point them the direction that the particle is moving, which is kind of like current, right? Rotate your hand until your palm's the direction of the field. Then your thumb will tell you the direction of the force if it's a positively charged particle. If it's a negatively charged particle, like an electron, it's just the other direction. You could think of other ways. You could just use your left hand if it's negative. I prefer just to say, hey, if it's negative, it's going to go the other way. But you might remember negative particles, use the left-hand rule. That's fine. Omer. Imagine I have an electron gun, okay, a gun that shoots electrons, and it shoots them really fast. It's like an electron machine gun. I didn't draw a machine gun, but that's what it looks like, okay? And imagine that I also have a target. And every time an electron hits my target, it gives off, it's a special target, it gives off a little flash of light. So if electron hits over here, little flash of light, okay? Now, in between, if you just sit there and aim, you're always going to hit it right in the middle, unless you place a magnet in between your gun and your target. Okay? And then you can control the strength of the magnetic field. Remember, as those electrons move through the magnetic field, they're going to curve, and I can control their curvature either by controlling the speed of the electrons or the strength of the magnetic field. Okay? And then if I placed another magnetic field that's perpendicular to this one, okay, right, and all my electrons have to go through there, so I have a vertical and a horizontal, and I can control those things. I can control where my electrons hit the screen, right, just by adjusting some variables. And I do it really fast. I shoot a bunch of electrons, and I control where they hit really, really fast, and suddenly I get these glowing patterns on the screen. And then I make those glowing patterns move, and suddenly I have an image running across my screen of someone with a gun chasing somebody, blowing up cars, and all that stuff. And we call it television, okay? This is how original television, old school television screens and computer monitors used to work. Okay. No, the vacuum tube I think had to do with the electron gun, and then there's magnets in here. If you remember, this is the kind of TV I have at home. I'm pretty old school with technology that way. I don't have a flat screen TV, but if you remember kind of the traditional original TVs. They have a big box kind of thing, you know, they're not flat, and then there's something sticking out the back usually, right? That's the electron gun. Okay, and there's magnets in here, there's your screen, all right? Color is great. If you have color pictures, I don't know if they have 3 deep screens or they just have one screen with 3 different target zones, and you have certain chemicals that instead of just giving off a white light, certain chemicals, when they get excited by an electron, will give off red light, others will give off green, and others will give off blue. And you have these things called pixels, little spots on the screen that are designated red, blue, and green, and they're all right next to each other, and they're really small. And so you can combine red, blue, and green light and form all the other colors that you need. And all right, so we just talked about old school television and computer monitors. Now, let's think about a situation here. Imagine I have a charged particle, and I inject it into a magnetic field. And it has a certain velocity. The magnetic field has a certain strength. Let's think about what kind of a path that particle will take. Okay? You're looking ahead. Well, that's good. How did you think? So Hayden's going like this. Why is that? How does, with this right-hand rule we've been using, how does the direction of the force relate to the direction of the motion? It's always perpendicular. And remember back to circular motion, you get circular motion when you exert a force perpendicular to the direction of travel, right? Remember that? So you get circular motion. And this reminds me of something else. Have you ever wondered about how we have this periodic table of the elements, and we say hydrogen, for example, and we tell you the mass of a hydrogen atom, okay? How do we know that? You can't take a hydrogen atom and stick it on a little balance in the lab and go, ooh, it weighs, 4/10 trillionths of a gram. No. They use this technology. It's called a mass spectrometer. If you inject a particle into a magnetic field and you know the velocity of that particle, and then you measure the radius of the circle that it carves out, you can find the mass of the object. Okay? And this is how they measure the masses of different isotopes and things like that. Okay? Does it look cool? I want to show you a picture. But before I show you a picture, I want to tell you one more thing. Okay? This is also how I say we like I do this, physicists explore the subatomic world. Okay? Particle accelerators. You've probably heard of CERN and the Large Hadron Collider. You might have heard of Fermilab in Illinois. These are big machines. Their sole purpose is to discover the fundamental building blocks of the universe. And the way they do it is by taking usually protons, but sometimes they take other things, getting them going really fast, smashing them together, and then trying to observe what comes out. Now, you can't see subatomic particles. They're too small. So how do you observe them? What they do is they have these collisions happen in a very special place. And there's different techniques, but the most common technique is called a bubble chamber. You have the collision happen so that the debris that comes flying out will go through a chamber that's super saturated. The air is like super, super humid, but it hasn't condensed in there. And so when the particles go through, they create ions, and then you get condensation. You get a trail of clouds, basically, behind the particle passing through, just like when a jet flies through the atmosphere and there's a contrail left behind. But it's a subatomic particle doing it. And then in that cloud chamber, you put a magnetic field. If the particle is charged, it will curve. If it's charged negatively, it'll curve one way. If it's charged positively, it'll curve the other way. If it's more massive, it'll curve less. If it's less massive, it'll curve more. If it's more charged, it'll curve more, and so on and so on. And they look at this kind of stuff and discover the subatomic world. Okay? This is a picture from a particle accelerator. This is the bubble chamber, okay, where a collision just happened. Subatomic particles smaller than protons were flying in all different directions. And some of them, and these are all just the trails left behind when they passed through the bubble chamber. Okay, there was a magnetic field. Notice that some of the paths are very straight. That was an uncharged particle. It doesn't feel a force by a magnetic field. It just moves right on through. Okay? But some of the particles have like crazy little curves. Dude, there's a little loop right there. There's one right here that's doing all sorts of crazy things. There's another one right there. And another one right there. Okay? And they do this enough, and you start analyzing the paths and everything like that. And this is how they discover pions and kaons and muons and all these other subatomic particles that are even smaller or different than the typical protons, neutrons, and electrons that we've always talked about. Omer. Okay. So here's the last slide. And here's the deal, you guys. This was you've already done these problems really with your intro questions. They were very much similar. So we're not going to do them now because I'd like to do a lab for a little bit. But I do want you to see a couple of things. You can try these at home if you want if you want to watch this video again. But a couple things to recognize is watch out for the common tricks. When you're using F equals BIL, remember that L is measured in meters, not centimeters. Okay? And let's see, down here, it just says a beam of electrons is moving at a certain velocity in a field, calculate the direction and the magnitude of the force. What would we use for Q in that case? The elementary charge, 1.6 times 10 to the negative 19. And if it was a proton, what would we use? The same, just positive. Excellent. Okay.